Hello, everyone. I'm happy to see you. Today we have Klaus Mattis from University of Mainz, who is going to talk about unstable p-completion of motivic spaces. Thank you.
Okay, thank you. Thank you for the introduction and thank you for having me in the seminar. Okay, yes, I'm going to talk about p-completion of motivic spaces. And for this, I should first tell you why p-completions are interesting in homotopy theory. And yes, at some point in history, algebraic topologists realized that things get easier if we do it like one prime at a time. And so if you have a spectrum X, you can associate to it this p-adic limit, where you take the limit over the quotients of X by the p to the n multiplication map, and this funny quotient is just the co-fiber of the multiplication by p to the n. So this is really the thing you know probably from algebra or somewhere where this was called like p-adic completion of a module, and now we do the same in the category of spectra. And what does this help us? Okay, the first thing is we can recover X from those p-completions. So we can put X into a Cartesian square, which is called an arithmetic fracture square. And here is the product over all the p-completions, and downstairs is the rationalization of X. So the thing with the rational homotopy groups of X, and here the rationalization of this guy. And then if we take the pullback of this part, then we recover X. So if we can prove something about the p-completions, that this can say us something about X. And there are lots of tools that we can use to study this p-completed spectrum. For example, there's the atom spectral sequence, which converges to the homotopy groups of this guy or something like this. And similarly, people found out that you can do this in the unstable world, that you take some anima and you can produce some xp hat here, which we call the p-completion of X as an anima. And for this, we also have a fracture square of this form, where we replace the spectrum X by the anima X, but then it's the same square. And we have an unstable atom spectral sequence, which can compute the homotopy groups of this guy and so on. And now the question you can ask is there an analog for other homotopy theories? So for example, if we are in an infinity topos, do we also have a p-completion process like this? Or if we are in motivic homotopy theory, can we do the same? And the short answer to this question, yes?
Just before you get too much into the completion, could you just briefly review how the completion of anima looks like?
Yes, I will do this more or less by doing it in an infinity topos where it is the same thing, but
perfect.
We will get to this later. Okay, but what I can say is that the homotopy groups of this guy look like the derived p-completion of the homotopy groups of this guy, roughly. Okay. So, but first, before I can talk about unstable p-completion in an infinity topos, I have to talk a little bit about stable p-completion in an arbitrary stable category. And so the setting for now will be that D is a stable and presentable infinity category. And if you don't know these words, then stable is more or less the infinity categorical term for triangulated. And presentable is more or less a condition that colimits and limits exist, and some set theoretic additional conditions, but this is what you should think about this D. And then we can say that a map in D is a P equivalence if it is an equivalence mod P. And again, this mod P guy is just the co-fiber of the multiplication by P map on X and Y. Okay, and if this is an equivalence, then we call our morphism a P equivalence. And now we can say that an object set in D is p-complete if it is local with respect to p equivalences. So this means if you take some p equivalence f in D, then f induces on mapping spaces from Y to Z to X to Z an equivalence. So these p-complete objects are exactly those objects which see p equivalences as equivalences. And then we can write dp hat for the full subcategory in D, consisting exactly of this p-complete objects. And then this is like a general fact. If you single out a class of things which are your weak equivalences or p equivalences or whatever, and you take the class of local objects here, then this is a localizing subcategory. And in particular, you get a left adjoint to this inclusion, which we will call the p-completion functor from D to dp hat. And this is the Bouwsfield localization, and this exactly inverts the p equivalences. And if we are in a stable category, then the funny thing happens that this p-completion functor has a very explicit description, because it is equivalent to this p-adic limit procedure, like in the case of spectra, where we just take the limit over the higher powers of the p to the n cofiber. Okay, so this is the general thing of p-completions in a stable category. And now if we are in the category of spectra, then Bouwsfield and Kahn showed in the 70s that if we take some spectrum X and a natural number N, then we get a short exact sequence of this form, where we put the homotopy groups of the p-completed spectra in the spectrum in the middle. And on the left and right, we have the homotopy groups of X, but we have to derived p-complete them. So this L0 and this L1 are the derived p-completion functors. So these are given by, I start with an abelian group here. So this guy is an abelian group. I can embed this into spectra by doing this Eilenberg-MacLane spectrum functor. Then I can p-complete the spectrum via this p-adic limit, and then I can take the nth homotopy object, or I guess the ith homotopy object, and then get back an abelian group. And these are then called derived p-completion functors. These are exactly the functors you probably know from some commutative algebra course or something. And these are the right derived functors of the normal p-adic completion functor on abelian groups. And you can show that these actually are 0, except in the case where I equals 0 or 1, and that they fit into this short exact sequence. And as a quick corollary, we get that if X is a spectrum which is n-connective, so has no homotopy groups below degree n, then also the p-completion is n-connective, because we see that the only contributions to the pi n of the p-completions are coming from the pi n minus 1 of X and pi n of X. And if we are 0 below n, then also these guys must be 0 below our degree n, because the outer terms are 0. Okay, and now we can ask if this is true for our general category D. And for this, we have to talk about what is an homotopy object or homotopy group in our category D. So we want to talk about this guy. And for this, we will equip D with a T structure. So we have a collection of connective objects and a collection of co-connective objects, and they satisfy some axioms. And if you don't know what a T structure is, then this is just a very general way to talk about homotopy objects in a triangulated or stable category. And we can then write D hard for the intersection of the connective and co-connective objects. And then the funny thing is, what happens is that this hard is no longer an infinity category, but is actually an abelian 1 category. So you somehow kill the higher homotopies, the higher homotopy groups of the mapping spaces between objects here. And yes, in particular, you then get some homotopy group functors from D to this hard by taking some object X. You take the n truncation of it with respect to this T structure. You take the n connective cover with respect to the T structure, and then you have to shift it by minus n to land in this intersection. But this is just the same thing which you do in spectra, but now in an axiomatized way. So for example, if you take D, the category of spectra, and the standard T structure, then these are just the normal homotopy groups, and the heart of D is just the category of abelian groups. And now we can ask if we have such a sequence in our category D, and the answer is no. For example, if we have some x in this connective part, then we can no longer expect that this limit is again connective, because so these parts will still be connective in any T structure, but it is unreasonable to expect that this limit preserves connectivity. And in general, this is very false. So you can find an example of a category D and an object X, which is connective, but where the P completion is not connective for any n. So not n connective for any n. So this, so a priori, it seems like there's no solution to find such a sequence, but there's a workaround. The goal, the idea is to introduce a new T structure in which this P completion process is well behaved. So what I can do is I can define the p-adic connective objects as those objects of D such that modulo P, so again this cofiber of the multiplication by P map, is connective in the T structure in which I started with. And then I can take the -1 co-connective objects as some right orthogonal complement of this guy. So you are in this guy if the mapping spaces from all objects here to your object are 0. Okay, this is what it is, and then it's a very general thing that this is again a T structure. You have to show that this guy is stable under colimits and extensions, and then you get a T structure. And we call this T structure the p-adic T structure associated to the T structure which we started. So this is now a second T structure, and we will define the p-adic heart as the heart of this new T structure, so the intersection of the p-adic connective and the p-adic co-connective objects. And similar to before, we get these p-adic homotopy groups, which are just take the truncations and connective covers in this new T structure, and then you get something in the p-adic heart. Okay, so we have this, and now we can define these black bold Li functors, which are the new derived P completion functors. And we start with some object in the normal heart, so in the heart from the old T structure, and then we can P complete it and then take the ith homotopy group with respect to the new T structure, and then land in the p-adic heart. And we can compare this to the old definition of the derived P completion functor, where we took the homotopy object with respect to the normal T structure. And you can now ask us, yeah?
Does this work for any category D to construct this T structure?
Yes, this is very general. You can do this in any stable category. Okay, and you can ask why do we do this, and then you can show that in this new T structure, these fancy derived P completion functors are 0 if you're not 0, if you're not in degree 0 or 1, and this is totally wrong for these LIs. Because for the reason I explained before, that if you start with something which is connective, there's no reason to expect that this is still connective. So you will get negative pi i's here. So there will be negative LIs, but with this new fancy LIs, there will be no negative LIs. So in particular, you get this part C here. If you start with something connective in a normal T structure, then the P completion will be connective in the p-adic T structure. And in particular, we can see, we can prove that for some X and D, we get a short exact sequence like in the Bausfield-Kahn lemma of this form, where we now have to take the new derived P completion functors here, and we have to take the derived P completed, the p-adic homotopy groups here, and then we get such a sequence. And yes, and this helps in computing stuff. So the slogan which you can learn from this maybe is that Bausfield-Kahn holds in the p-adic T structure. So, and one thing you can ask is, okay, if we go back to the category of spectra, does this give something new, or is this the same? And it turns out that in our special case where D is the category of spectra, this T structure and this new result recovers the original Bausfield-Kahn lemma, because here we see that the p-adic heart is actually the intersection of the normal heart with the p-complete object. So these are exactly abelian groups which are derived p-complete, and using this we can identify the old derived p-completion functors with the new derived p-completion functors, and actually we can compute the p-adic homotopy groups of some spectrum X by taking the normal homotopy groups of the p-completion of some spectrum X. But I have to warn you that in general, in a general category, all these three isomorphisms are totally wrong and will not be true. But if you take those things and plug them into this sequence here, you can see that we will recover the old sequence from up here. Okay. So this is for the beginning all I want to tell you about stable p-completion, and we will use this to define unstable p-completion. So we will now be in the following setting. X will always be an infinity topos, and if you are not sure what this really is, you can think of this as sheaves on some category C with respect to some Grothendieck topology tau, and these are sheaves of anima instead of sheaves of sets. And if you don't know what a Grothendieck topology on a site is, then you can think of this as maybe the category of sheaves of anima on some topological space X.
Before we get too far into the unstable case, there's another question in the chat. So there's another definition for p-completion of E-infinity ring spectra, where the p-completion is the totalization of the spectrum wedged with the HFP wedge blank of the co-simplicial spectrum given by smashing X with the co-realization of HFP. Do you know does that agree with the one you talked about here?
I guess in spectra this should give you the same thing, but in other categories I'm not sure.
Okay.
But as far as I'm aware, in spectra this is the same thing. Yes. Okay. So now our setting is that we have an infinity topos X, and to any infinity topos we can associate a category split of X, which we call the stabilization of X, and this is given by the limit over taking the iterated loop space on pointed objects in X. And if you plug in the category of anima here, then this is just the usual definition of the category of spectra. So this is the generalization of the category of spectra to an arbitrary infinity topos. So you can show that this category is stable and presentable. And in particular, there's an adjunction here given by the right adjoint. Is called the infinite loop space of some spectrum object here. This is just given by going to the last component of this limit. And this has a left adjoint called the suspension spectrum of a sheaf X. Okay. And now we can use this adjunction to define what a p equivalence in X is. And this also explains how we define p-complete objects in anima by starting with a morphism here in X, and we say that it is a p equivalence if its suspension spectrum is a p equivalence. So we go to the stable category, and if we are p equivalence there, then we are called a p equivalence in X. And just to remind you, a p equivalence in the stable category just means that we are an equivalence modulo p. And we say now that an object Z in X is p-complete if it is local with respect to those p equivalences. So again, the same definition as before. If for every f which is a p equivalence, f induces an isomorphism on mapping spaces. And then again, we can write xp hat for the full subcategory of p-complete objects. And again, the general theory of localizations gives us that the inclusion has a left adjoint, which we denote by this p-completion symbol. And this is exactly the functor which inverts the p-equivalences and is universal with respect to this property and is a Bose field localization and so on. Okay, so from abstract theory, we get some notion of p-complete objects and some notion of p-completion functor. But now the question is, how can we ever compute something like this? And the big problem is that in the unstable world, there is no such formula of the form x is mapped to this p-adic limit, because we can't even say what is the multiplication by p morphism on x. There's no such thing. So the question is, how can we ever calculate this guy? And the idea is that we try to reduce it to the category of spectra where we have this easy limit formula. And okay, the first thing is where we want to look at is to see how we can p-complete an Allenberg-MacLane sheaf. So if we have an A in the abelian group objects of the discrete part of X, so if X is our topos, so it's sheaves on some side, then this guy is just sheaves of sets on the same side. And then we take an abelian group object in it. So this is nothing else than sheaves of abelian groups on this side. And if we have such an A and we have an N, then we can form the Allenberg-MacLane space of A in degree N, or Allenberg-MacLane sheaf, I guess. And this is just a sheaf in this topos such that its nth homotopy group is A and the other homotopy groups are 0. And we can ask what happens if we p-complete this guy, because this is close to being a spectrum, because this Allenberg-MacLane space is actually the infinite loop space of the suspension of the Allenberg-MacLane spectrum of A, so like in topology. And then if we want to p-complete this guy, then there is an explicit formula. So we first p-complete this guy in the stable category, and then do the same thing as here, take the infinite loop space. And for some weird reason, we have to take the connected cover, so throw away the components which do not contain a base point. And that's how it works. And now this thing is easy, because for this we have this very explicit formula with this limit here. Okay, so at least for Allenberg-MacLane sheaves, we can understand p-completion. And now the goal is to somehow get from Allenberg-MacLane sheaves to general sheaves. And okay, how to do this? So first, suppose we start with an X which is connected and n-truncated. So connected and n-truncated just means that the pi 0 is trivial and the pi k's are trivial for k bigger than n. And then as in topology, we have a fiber sequence of the form where we have X here. We can have the canonical map to the n-1 truncation of X. So this is just the object which throws away the nth homotopy group but keeps the others. And if we take the fiber of this map, then we get an Allenberg-MacLane sheaf, which has the homotopy group, the nth homotopy group of X in degree n. And now a funny thing happens if X is moreover simply connected. So if pi1x is 0, then we can rotate this fiber sequence and put this guy to the right to recover X as the fiber of the n-1 truncation of X via some map to the Allenberg-MacLane sheaf of pi and X in degree n+1. And so now this is a limit of these guys. And this can help us to compute the p-completion of this guy by first p-completing this guy, and then taking the fiber. And probably what I should say is that something similar is more generally true for if we take X nilpotent, and if you know what a nilpotent space is, then you can do the same definition in an arbitrary infinity topos. And then you also get something like this rotation result. And everything from now on is also true for nilpotent X, but for simplicity, I will only assume that X is simply connected, because then we don't have to care about the pi1 stuff. Okay, so now we have this fiber sequence here, and we can use this now to calculate the p-completion of X by first p-completing the n-1 truncation of X, and then p-completing the Allenberg-MacLane sheaf, taking the fiber of this p-completed morphism, and then again, for some weird reason, we have to throw away the components which do not contain a base point, but doesn't really matter. And so this is how we can compute the p-completion of X. And so we know how to do this. This was the formula with by taking the p-completion in the stable category and then taking the infinite loop space from before. And now by induction, on the n-truncatedness of X, we can calculate this by calculating this and then going down. And at some point, we will have the one truncation of X. And since X is simply connected, it will be the trivial space, and the p-completion of the trivial space is the trivial space. So we are now able to calculate the p-completion of any simply connected n-truncated space. And now you can ask, what if X is not truncated? And in anima, what you do is you can take the Postnikov tower and write X as the limit over the Postnikov tower. And in a general infinity topos, this is not possible, but we say that an infinity topos X is Postnikov complete if X as a category is isomorphic to the limit over the subcategories of X consisting of the n-truncated objects. So the morphism from here to here is just induced by going from X to the n-truncated objects by n-truncation on each component. And then this gives you a map, and you require this map to be in equivalence. And if we are Postnikov complete, then we can write every, yeah?
Do you mean that extension problems or K invariants are easy to control? It's a question from the chat.
I mean, I think it's not easy, but I mean, at least we know that we can do this if we are simply connected. If we are not simply connected, or if we are not nilpotent, then there's no reason to expect that this fiber sequence exists. Also, maybe what I should say is that by how to calculate p-completions, I don't mean that you start with some space and you can explicitly calculate the space you get by p-completion, but it's more like a tool which you can use in proofs to like say something about how the p-completion works by reducing it to the simpler case of p-completion of Eilenberg-McLean sheaves. Okay, where was I? Okay, here. So if we are Postnikov complete, then every X can be written as the limit over the n truncations of X. So this we get out of this, implies that also this is true. And now you can hope that if I p-complete this, then all I have to do is take the limit over the p-completions of these guys. And this is almost true. So the theorem is if X is a Postnikov complete infinity topos plus some finiteness condition, which I will not explain, then we can calculate the p-completion as the limit over the p-completions of the truncations, at least for simply connected X or nilpotent X. And the clue now is that we know how to say something about this, because this is now simply connected and n-truncated, and we can use this inductive process here to say something about this guy. Okay, and then you can maybe ask for which X is this actually satisfied, and there are some examples, for example, the category of anima or the category of pre-sheaves on some category C. But more important for me, who is doing motivic homotopy theory, are the Zariski and the Nesnevich topoi on smooth schemes, which I will explain later. Okay. So now we have talked about how one can calculate something about p, how one can prove something about p-completions, and now the rest of the talk I will try to explain how we get a short exact sequence of the type of this how like in the stable case, this Gauss-Wilcan short exact sequence, how we can get something like this in an unstable world for motivic spaces. So the first thing I should do is explain to you what a motivic space actually is. So we will start with a perfect field K, and we denote by smooth K the category of quasi-compact smooth K schemes. So if you don't know what a K scheme is, you should think of objects in there as like a smooth manifold, but now over our field K. Okay, and now we want to define a Grothendieck topology on this smooth schemes K. And for this, we say that a family of morphisms Ui to U in smooth K is in a Snevich cover if this index set is finite. Each of these morphisms Fi is étal. Étal is just the algebraic geometric version of covering space. And for every x in U, we want to find, we require that there's some I in I and some y in Ui, such that Fi maps y to x. So this just means that these maps are jointly surjective, but we want a little bit more. We want that actually they have the same residue field via Fi. So as a quick example, for example, the morphism from spec C to spec C, which is given by the identity, is in a Snevich cover because this induces the morphism C to C on residue fields. But the morphism from spec C to spec R is étal, but not Snevich because this is not a isomorphism on residue fields, but it still is a I guess separable extension, and separable extensions are étal morphisms. Okay. Now we know what a Nisnevich cover should be, and now we can define the category of Nisnevich sheaves to be the category of sheaves, or the infinity topos of sheaves of anima with respect to the Grothendieck topology on smooth K given by Nisnevich covers. Okay, and now I can define what a motivic space is. So if we have some X living in this Nisnevich sheaves, then we say that it is a motivic space, or it is A1 invariant if the morphism from X evaluated at U to X evaluated at U times A1, the affine line, induced via the projection from this guy to this guy, is an equivalence for all smooth schemes U. And just to remind you, the affine line is just the spectrum of the polynomial ring in one variable. And so this A1 invariance is like the algebraic geometric version of being homotopy invariant. So in topology, you would probably say that some functor is homotopy invariant. If I evaluate some functor on a space X, then this gives you the same result as if I evaluate it on X times the interval. And in algebraic geometry, we replace the interval by this affine line. Okay, and we will now write spaces K in Nisnevich sheaves for the full subcategory of motivic spaces. And similar to the P completion stuff, we get that there's a left adjoint LA1 from Nisnevich sheaves to motivic spaces, which is a left adjoint to the inclusion, which is the functor which inverts A1 equivalences. I should warn you that this guy is not an infinity topos, and this guy is not left exact, so does not commute with finite limits. So if I have a motivic space X, then the P completion always means P completion in Nisnevich sheaves and not in motivic spaces, because this is not an infinity topos. Okay. So the first thing you want to prove is that if you have some motivic space, that if you P complete this guy, then it stays A1 invariant. And this is true, at least if you are simply connected. And simply connected just means that you're simply connected as a Nisnevich sheaf. And then we can use the inductive process and the limit process from before to reduce to the case of Eilenberg-MacLane sheaves. And there you can explicitly see that the P completion stays A1 invariant. So, okay, we at least get some P completion functor on motivic spaces. And now I want to talk about the short exact sequence. And now I have to backtrack a little bit to go to first the case of anima. So in anima, Bousfield and Kahn also showed that if you have a simply connected anima and an integer n bigger than 2, then there is a short exact sequence in abelian groups, which is the heart of the standard T structure and spectra of the form where I derive P complete the homotopy groups here, and I have the homotopy group of the P completion in here. Okay, And we have seen before that these guys are actually in spectra equivalent to those guys here, and to those fancy derived p-completion functors here. And from this, we see that actually this short exact sequence is living in the p-adic heart, so in p-complete abelian groups. And now the goal is to get a similar sequence for motivic spaces. And the strategy is to look at the...
Sorry?
Yeah.
Before you move on to the next case, were you using the fact that K is a field, and in particular that it's perfect?
Until now, we didn't use this. So you can do everything here for any base scheme S, I guess. But yeah, later things will only be true if you have a perfect field as your base. Okay, so the strategy is to look at this diagram. So here is the category of motivic spaces. Here is where I want to do some p-completions, but p-completions here are hard because of these connectivity problems I talked earlier in the stable case, which we also have in the unstable case. And so the idea is to reduce it to some easier case of p-completions where we know what happens. And so the idea is to first go to Nisnevich sheaves and then go to Zariski sheaves. So there is also a topos called Zariski sheaves, which is where we replace Nisnevich covers by Zariski covers, and Zariski covers are just given by open immersion, so open covers of some scheme. Okay, and the idea is to embed this now in the pro-Zariski topos. So if you have heard of the pro-etal topology, then this is the same thing as in the etal topology version. This is the Zariski version of the pro-etal topology, where we embed our Zariski topos in some big topos of pro-Zariski sheaves. And this guy is very easy because this is compact projectively generated, so it's isomorphic to some p sigma on some category W. I will explain what this p sigma guy is. And then we can go to a category of pre-sheaves on this W. And here p-completion is easy because in pre-sheaves, p-completion is just p-completion on each level. So this is just p-completion of anima, which we know how to do, and there are no connectivity drops by p-completing.
And here W is what?
I will come to this, what this W actually is. Okay, so I try to explain what this top row is, but I guess for time reasons I will skip the part about this pro-Zariski topology, how you can define this, and just say what the main theorem about this pro-Zariski guy is. So as I said before, you can embed the Zariski thing into some pro-Zariski guy, and now the idea is that there is this subcategory W of weakly contractible objects, which are compact projective generators, such that the pro-Zariski topos is isomorphic to this p sigma guy on W, and this p sigma guy on W is just pre-sheaves on W, which preserve finite products. But because we have an opposite here, this just means that it takes disjoint unions in W to a product in anima. And then you can also show that this is the same as sheaves on W with the disjoint union topology. So covers are given by disjoint unions of schemes. And the idea is what are these weakly contractible objects? So if you know some condensed mathematics, then you have maybe seen that you can embed sets into the category of condensed sets, or similar, you can embed anima into the category of condensed anima. And this is similar to condensed anima, and this is then similar to anima. And in condensed mathematics, you can show that condensed anima is isomorphic to p sigma of W, where W is the category of extremely disconnected compact Hausdorff spaces. And here, a similar thing is true. This pro-Zariski guy is isomorphic to a category of schemes, is isomorphic to the p sigma on some W, and W is given by schemes over K. such that the pi zero of these schemes, so the topological pi zero, is a extremely disconnected compact Hausdorff space. So this is similar to the condensed mathematics stuff. And now I can explain you how we get this short exact sequence by going from here down to here. And yes, on this pre-sheaf guy, the short exact sequence is really easy, as I said before, because we are just a pre-sheaf topos, and here everything is calculated level-wise. So the p-completion is calculated on each level, the homotopy groups, the derived p-completion functors, and the p-adic hard. And so applying this level-wise Bousfield-Kahn theorem, we get a level-wise Bousfield-Kahn short exact sequence, and everything is functorial. So we get a short exact sequence of this type here in the p-adic heart of the stabilization of the pre-sheaf topos. Okay, and now we have it on this PW, and we want to have it on this P sigma, and this is also comparatively easy because this inclusion functor from P sigma to PW, which just forgets that our sheaf here is product preserving, this preserves P equivalences and P complete objects. So one can show that it actually commutes with P completions and those derived P completion functors. And in particular, we again get that this p-adic heart of the stabilization of the P sigma guy is living in the normal heart. And then we can use the same sequence from here. And if we start with something in P sigma here, then everything here lives also in this P sigma world, and we get this short exact sequence here. Okay, this is the not so important and easy part. And now you can ask how to get it from here to down here. And just to recap, we are now in this situation where we want to have something that's a risky topos, and that's a risky topos embeds into this P sigma of W guy where everything is easy. But the problem now is in the Zariski world, this p-adic heart is no longer inside the normal heart because of these connectivity problems. And therefore, we cannot expect that we have such a sequence on the nose, because this guy is living in the normal heart, and these guys are living in the p-adic heart. So, like, maybe they live in the intersection, but this is totally unclear. So what we need is a replacement for this guy, which is living in the p-adic heart. And we can use the following definition. So for some Zariski sheaf X, we can just define a p-completed the p-adic homotopy group of X by going up into the pro-Zariski topos, p-completing there. This is the easy stuff. Then take the normal Pn, the normal pi n, which is actually living in the p-adic heart, as we saw before, and then pushing this down to Zariski sheaves. Okay, this is some definition, and we can say something about this. So the first thing is if we have a p equivalence between objects x to y, then F induces an isomorphism on these p-adic homotopy groups. So in particular, the p-adic homotopy group of X is the same as the p-adic homotopy group of the p completion of X. And much more important, we get the converse. If we start with a morphism of simply connected sheaves that is an equivalence on p-adic homotopy groups, then F is already, oh, this is wrong, F is already a p equivalence. And so this is what you could call probably a p-adic Whitehead theorem, that if we have an equivalence on p-adic homotopy groups, we are already a p equivalence. Okay, and we can now ask if this p-adic homotopy group is actually living in the p-adic heart, because we are here in the p-adic heart, but okay, we have to push it down. Are we still in the p-adic heart? And the answer here is in general, no. But there is some formula which we can use to check if this is true. And it turns out that this guy is living in the p-adic heart exactly if this guy, so we take we go with X. So we take X and go to the pro-Zariski guy and p complete there and take the normal homotopy group. So if we would now push it down to the Zariski topos, then we would get this guy. but we can also derive p-completed here with this L1 guy, and then mod out p and ask if this guy is living in the essential image of nu upper star. Okay, this is some very weird and very technical condition, but what does this actually say? So you can explicitly calculate this guy, and then you see that this guy is actually just measuring the unbounded p-power torsion of this guy. And if you know some stuff about p-completions in spectra, then you will know that p-completions always get tricky if unbounded p-power torsion is involved. And that this guy is living in the essential image here just guarantees that if this guy has pro-Zariski locally unbounded p-power torsion, then this unbounded p-power torsion can already be detected Zariski locally. And I can say what this means in technical terms, but maybe because of time I will not do this. But what you should get out of this is everything is good if this bad unbounded p-power torsion comes always from the topos in which we started with. And if we use this, we can get a short exact sequence in the p-adic heart of the Zariski topos of this form if we start with a simply connected X which fulfills this weird criterion. Okay, and now you can ask, is this criterion, is this condition ever satisfied? And now the thing what happens is, yes, it is satisfied by motivic spaces, and you can ask why. And the idea is if you start with a scheme U, which is smooth, and U is connected and has generic point eta, and you have a motivic space X, then there is a result by Gabber that for every K, there's an injective morphism of this form where you start here with the homotopy group of X mod P to the K and evaluate at U, and you go here to the generic point. This is called Gersten injectivity or exactness of the Gersten complex, and this was more or less proven by Gabber with other words, but more or less this is his result. And we see that this guy is living in smooth schemes, and somehow I didn't explain this, but this guy is living in this pro-Zariski topos guy. And so we see that if you want to say something about p-power torsion in the pro-Zariski world, then this injective map helps us to detect it in the smooth, in the Zariski world. And if we use this lemma from Gabber plus something else, which I cannot tell you right now, is that we get the following theorem. If we start with a connected motivic space, which is simply connected, and we have some n bigger or equal than 2, then we get a short exact sequence in the p-adic heart of the Nesnevich topos of this form here, where we again have the p-completed homotopy groups of the p-completion of X here, and here the new derived p-completion, the new derived p-completion of the homotopy groups of X. Okay, and I guess this was my talk.
Thank you very much. I will